Okay, today we're going to talk about a method for solving equations called the secant method. It's fairly simple and it has useful applications. So the problem we're trying to solve is finding the value x that makes g of x equal to 0. And the secant line is simply a line that intersects the curve in two or more places. We'll use that as a proxy for g of x. We find 2 points on g of x. We use a line. We find out where it intersects the x-axis. And we go on from that. So, okay, here we have the curve, and we're looking for the green dot, the place where the curve intersects the x-axis. So how would we do that? Well, we need to find 2 points. These are the pink points there. 2, 2, 3, 7. We calculate the slope, which is 5. And then we find the value of the red dot, which is 1.6. Now that we have a new value of x, this is the x3 value, we can throw away the x1 value and use the x2 and the x3 values to get another estimate. So that's what we're doing. The 2 points now are the x2 value, which is the 2, 2, and the x3, which is the 1.6, 0.56. Calculate the slope, solve for the red dot, which is 1.44, which is closer to the green dot, which is 1.41. By iterating, we can get a desired precision. Okay, so first step of doing the secant method, you have to find 2 initial points. How would you find 2 initial points? Well, you could use fixed point iteration to get these points. Second step, you want to compute the slope. That's straightforward. The change in y value divided by the change in x value. Third step is you find the secant line and intersect it with the x-axis. That's straightforward. The secant line is uses the slope we just calculated, and you find x, the new value of x, we'll call it x3. And if you look at the formula and you know Newton-Raphson, you'd say, it's almost exactly the same thing. The difference is that we're using the discrete slope calculation instead of the derivative. So you iterate on this until you get the desired precision. Now, why would you use the secant method when Newton-Raphson method is available? One obvious reason is, well, you have to walk before you can run. And if you don't know calculus, you really don't have any choice. You have to start with the secant method. That's what you would know at a high school level. But the second reason is that maybe g of x is something the computer can calculate, but you can't calculate without the computer, and you don't really know how it's computed, so you don't know how to differentiate it. But the third reason is perhaps the most relevant. Sometimes g of x, the derivative, is computationally burdensome to compute. And if you don't have to compute the derivative, why bother? The secant method is a way of finding solutions to these problems without bothering with the computational burden of a derivative. Here's an example. Suppose you find g of 1, of g of 2, of g of 3, etc. That would be such a mess to differentiate. Why bother? You don't have to. You can solve this problem without it. Okay, we'll give some examples, but these examples are ones that the Newton-Raphson method would work really well with. But we'll use the secant method just because that's what we're talking about here. This problem comes up in trigonometry. The fixed point method, just basically you're solving for x and iterating. And we'll go to the spreadsheet and implement this. It's a very simple problem. Turns out that if you choose s equal to 0.5, you're solving for sine of 10 degrees. So it turns out to be about 0.17. So the fixed point problem, you're going to take the parameter divided by 3. Then you're going to add 4/3 times x cubed and just iterate on that. And you actually can get a pretty good value this way. But we'll also solve it the secant method. That's what's happening on the right-hand side. So we'll take the first two values because we needed 2 estimates to get the thing going. And the formula that we have to type in for y is the parameter s minus s actually, plus 3x minus 4x cubed. If we type this in correctly, we'll get a number fairly close to 0, and it will get closer to 0 as with each iteration. So we calculate delta x and delta y, and the slope. We'll use an if statement to avoid dividing by 0. And it's the change in y divided by the change in x. And then the adjustment, we'll use an if statement to avoid divide by 0. And the adjustment is the value of y minus the value of y divided by the slope. And then the new x is the old x plus the adjustment. And if we bring these calculations down, we should see that it converges pretty rapidly. Okay, there it is. That's the answer. Now, this is interesting. If you take the natural log of the absolute value of the adjustment, you'll see an interesting pattern emerge. Basically, the third number is close to, but not exactly, the sum of the first and the second number. That's what we're doing with that Fibonacci thing. It looks like a Fibonacci sequence. And that means that the ratio of these numbers approaches 1.62, which is the golden ratio. Not exactly. It's an approximation, but it's close. And if we put in different values, we'll see it's still close to 1.62. Okay, here's another example. This example comes from finding the fifth root of 1 plus a minus 1. Comes up in some applications. We can formulate it as a fixed point problem, and it works for small values of a. In this case, we're just going to modify the example that we just calculated so that we don't have to duplicate all that work. We just change the value of the fixed point problem. In this case, it's the parameter divided by 5 and then minus 2 times x squared minus 2 times x cubed minus 1 times x to the fourth minus 0.2 times x to the fifth. That was the formula that we said was the fixed point formula. And if we type that all correctly and bring it down, we'll get close to the value that we want, which is about 0.07. And we can use the first two values here, but we have to change the y values. And the y values here is minus the parameter plus 5 times x plus 10 times x squared plus 10 times x cubed plus 5 times x to the fourth plus 1 times x to the fifth. We type all that in correctly and bring it down. That's all we'll have to do to solve a completely different problem. Okay, it worked. Now we're solving for a fifth root. Notice that we still see the same Fibonacci type pattern in the errors. It's a common thing with all these examples, with every example. It's not exact, but it's close.